thank you so much for the kind introduction. I'm just so happy to be here to talk to you about this new curriculum laboratory seminar that we're planning to run in the fall this year. So I want to confess, or maybe let you know, this is my first time running one of these seminars. So I'm just really excited to be a part of this program. I think it's a spectacular program and is going to be an amazing opportunity. So the title of the seminar is going to be How Critical Elements Make Up Our Modern World. And the way that this is generally going to be structured, from my standpoint, is in this choose your own adventure format, where we will have sort of a theme for a given week's session in the program that we will be organized around, and folks will be alerted to the different content that's going to occur over the course of the semester, and then they can decide to which of the events that they would like to attend to build up the curricula and develop new content. And so this generally will focus on chemistry and physics, potentially, just as well as sort of general science instruction. And this theme is around critical elements. Okay, so what do I mean by that? So I've got a few slides put together here, and I just wanted to start out, since this is the first time I've delivered one of these. You gave such a nice introduction, Edward, but I wanted to give you a little bit more background material about me coming into the program. I'm an inorganic chemist. I've been teaching at Penn since 2009, so for about 12 years. Prior to that, I did a postdoc at Los Alamos National Laboratory, which is in beautiful northern New Mexico. And I did my PhD work at Texas A&M University prior to that. And as you said, Edward, I am involved now as the director of this Center for Sustainable Separations of Metals. And that actually is one of the important themes in my research program, is thinking about where stuff comes from in the world that enables our modern society. Okay, so for example, we work in the chemistry of rare earth metals, which some of the folks on the call may have heard of before. And they're actually really useful in a number of different technologies. And so one of the primary scientific questions that we have is, after we use a cell phone or after we use a computer, can we develop new chemistry that will help us to extract those materials from devices and use them again, instead of doing mining and having the environmental and pollution problems that go along with that? So it turns out that many of these, in fact, nearly all of these critical metals are recycled at extraordinarily low rates. So there's a real opportunity for science and engineering to make an impact for these vital metals that we use all across society. So I'm going to talk about that a little bit more, but just to give you a sense of the flavor of the research interests that I have in my research lab at Penn. This is a picture of my group, and also this NSF center that I work with a variety of investigators at 5 different universities to try and achieve outcomes related to the recycling of critical metals. Here's my group website and our Twitter feed if you care to follow some of our stuff. So as I said in the course description, this course is about exploring connections between chemistry and physics and their presence in our daily lives as materials that comprise sort of ubiquitous electronic devices, and furthermore, the environmental and human health aspects of the supply chains of these critical metals. So people have heard of the somewhat mysterious term, these rare earth metals. There are actually many other kinds of metals that are chemical elements that are essential for making up these modern devices and materials that go into these devices, but also impact things like renewable energy, electric cars, imaging in medical applications, in MRIs, for example, and in displays and many other applications. So there are a lot of desirable properties, chemical and physical properties, that come out of rare earths, but at the other side of them is that they have a huge pollution associated with their primary mining and production. And so we can use the fundamental chemistry at the high school level and at the junior high level to understand the properties of the elements and make connections with why the pollution is so bad or why we have to exert so much energy to purify these things. And so that's the kind of connection that I want to make. We want to follow the supply chains for these elements back to their source. Where do they come from? And how does it impact the people in the local communities who are maybe doing the primary mining of these things? And finally, to discuss opportunities for science and engineering to improve the landscape. So how can chemistry be developed that will, improve the environmental sustainability of the mining, reduce the impact, and also enable recycling? We recycle aluminum cans at a pretty high rate, so why can't we do that with rare earth metals from cell phones? So these are the kinds of themes that I'm interested in. And a lot of, for science students and students in introductory chemistry courses, we have the iconic periodic table. I mean, that was really an on-ramp for me and for many others. And I think students generally are interested in this iconic picture of the periodic table and what it means, right? And so there's a lot that we can make connections between for concepts of periodicity and why we fit the periodic table together in the way that we do, why are the elements organized in this way. We can fit that together with these challenges associated with critical materials and also the devices that the elements go into. And so I've circled the rare earths here for anybody who is curious. These are the rare earth metals, these 17 elements comprising the lanthanide, scandium, and yttrium. And so this is in sort of the weird sub-basement of the periodic table that most people never even talk about or are interested in. But there's actually, as a student, it's like, I want to know about gadolinium. I want to know about dysprosium, right? These weird things that are sort of in different parts of the periodic table. And I want to know something about those elements. And so, we talk about in chemistry that periodicity and how we can how we organize the periodic table in that way based on electrons buzzing around these atoms. But it turns out the flavors of the elements or the flavors of the electrons really dictate the properties that we can make a connection to for their use in applications like permanent magnets. So the rare earths here are at the bottom of the periodic table are in the F block, right? Or the fun block of the periodic table, as I like to call it. And so here in the F block, the orbitals that these electrons reside in have specific characteristics that translate directly into, what the solids look like and the properties that they deliver. So these weird elements like samarium, gadolinium, praseodymium, cerium, lanthanum, and neodymium. Those electronic properties translate directly into the application of these metals in things like wind turbines and electric vehicles. We already talked about cell phones, photovoltaics, rechargeable batteries, and energy efficient lighting. So there's also a strong connection to make here with climate change, sustainability, and renewable energy. And meeting the energy needs nationally and of the world going forward is going to be dictated in a significant way by our ability to obtain these critical materials and ultimately to attain them sustainably and perhaps to recycle them. So there are issues here that we can draw with sustainability and climate change in terms of curriculum development as well. And ultimately, this arrives at people and how people interact, for example, in terms of trade between different countries and where these elements are located. And the fact that they are critical, that means they have some use and they have some risk of supply. So that's typically thought of as a function of their potential to be disrupted and their ability to be traded and their economic vulnerability. So that's involved with people working with each other or not in terms of the capacity to produce these critical elements and trade them between nations. So I've already talked about the environmental challenges and the pollution that is caused and how people in a local way deal with it, and actually how a lot of the critical materials that we obtain and we use on a daily basis are rather exploitative of people in local communities around the world. This is a picture of folks who are doing mining in the Democratic Republic of the Congo in order to bring us cobalt that you and I use every day in our smartphones. Lithium extraction is also in this context for rechargeable batteries coming out of South America. So really all kinds of issues from the periodic table as a window and as a starting point, all the way down to, a global social justice movement related to obtaining critical materials in a non-exploitative way. So a real rich landscape of issues to explore related to fundamental chemistry. And this kind of encapsulate, I'm going to come back to that, this kind of thinking is encapsulating sort of the pedagogical philosophy that I'm becoming interested in related to this course material and curriculum development. And that is using a systems thinking approach with regard to fundamental chemistry concepts. So we want to, and this systems thinking is an approach for examining and addressing complex behaviors and phenomena from a more holistic perspective. How can we understand chemistry in the context of the impact that mining will have on people and the use of smartphones on a daily basis and wanting to deploy renewable energy in a more significant way. This is what we're after in the development of this course curriculum material is forest thinking. I like this particular system thinking skill rather than just, compartmentalizing chemistry, which is, I think, an aspect that many of us, myself included, fall into in chemistry curricula, is just teaching thermodynamics or just teaching electron configurations without having a better sense of the whole that we'd like to engender with the students. So that's pretty much what I wanted to say about how the course or what the course will be about this fall. I'm happy to answer any questions. I wanted to point to a little bit more material for an event that I did a couple of years ago that is posted online. If you care to maybe get a little bit more sense of this from sort of a speaking to the public standpoint. And so anyone can go and watch this event that I recorded with one of our local museums, a partnership with that museum, the Science History Institute in Philadelphia. And this event was called Rare Earth Elements, the Intersection of Science and Society. You can find it on this Vimeo website here. And you can happily reach out to me and I can give you more information about this event and others if you'd like. But in any case, this is the thinking that we have going for the course into the fall. And I'm just so excited to work with you all, and I'd be happy to answer any questions.